Hello everyone. I'm starting a new series, book reading series. I will be walking through my first book, which I have decided Theory of Computation. Theory of Computation is very necessary because I want to later on dive into compiler design and stuff. Uh, I thought why not start with TOC and then okay, let's see. So if you want to download this book, I actually can't put the download link in description because my channel isn't verified. Uh, but if you want to download this book, this is open source, and just search TOC by Sipser, and you will get a lot of links, open source links, and you can download. So yeah, starting with the book. Wait, let me just still exploring. Hello, hello. Welcome to the stream. So yeah, this is a very famous book by Michael Sipser. Let me erase this. Let's go through content. There is a chapter 0 also. Wow. Okay. I remember studying TOC course in college, which was totally shit, waste of time course. But in that course, the order was quite reverse. We studied regular languages at last, if I remember correctly. Yes, so that means this book is reverse. We are studying regular languages first. Okay. So introduction, regular languages, context-free languages, then church Turing thesis, decidability, reducibility, advanced topics in computability theory, then time complexity, space complexity, interactability, advanced topics in complexity theory, and that's it. 10 chapters, almost 500 pages, and we will be done. I hope to do this stream for almost 1.5 hours. So let's see. I haven't made any predefined goal that I have to study this much pages. We'll just explore how much we can do, walk through properly, solve which problems and stuffs. Preface, first edition, second edition, where's the third edition? Intro to TOC first appeared as a preliminary edition in paperback. Okay. The first edition differs from preliminary edition in several substantial ways. The final three chapters are new. Okay. In third edition, chapter 8, 9, and 10 are added. Chapter 6 was expanded also to include several advanced topics in computability theory. Other chapters were improved through inclusion of additional examples and exercises. And comments from instructors and students who used the preliminary edition were helpful in polishing chapters 0 to 7. Of course, the errors they reported have been corrected in this edition. And chapter 6 and 10 give a survey of several more advanced topics in computability and complexity theories. They are not intended to comprise a cohesive unit in the way that remaining chapters are. Okay. These chapters are included to allow the instructor to select optional topics, okay, that may be of interest to the serious student. The topics themselves range widely, some such as Turing reducibility and alteration are direct extensions of other concepts in the book. Others, such as decidable logical theories in cryptography, are brief introduction to large fields. Okay. Well, I do want to study cryptography. A long time ago made a roadmap for studying cryptography, but I only studied a couple of ciphers. Uh, I remember Caesar cipher. Okay, I think it's just swiping with matlab, numbers like the letter E is 5, so you put 5, I guess, if I'm right. And a couple more ciphers, I don't remember. I would like to enter into cryptography as well later on. Let's see if this book can help us. Okay. Okay. There are longer forms of prefaces. Chapter 0 is here. Okay. We begin with an overview of those areas in TOC that we present in this course. Following that, you will have a chance to learn or review some mathematical concepts that you will need later. Hmm. Automata, computability, and complexity. This book focuses on three traditionally central areas of TOC: automata, computability, and complexity, and they are linked by the question: what are the fundamental capabilities and limitations of computers? Okay. I remember this being the very profound question, and I can't navigate graphics tablet. I can't navigate my Zoom. Okay, fine. This book focuses on three okay, automata, computability, complexity. What are the fundamental capabilities and limitations of computers? This question goes back to 1930s when mathematical logicians first began to explore the meaning of computation. Technological advances since that time have greatly increased our ability to compute and have brought this question out of the realm of theory into the world of practical concern. In each of the three areas, automata, computability, and complexity, this question is interpreted differently and answers vary according to the interpretation. Following this introductory chapter, we explore each area in a separate part of this book. So you mean there are three parts in this book, right? If I if I say syllabus again, yes, we have part one. Yes, we have part three, and part three is the last part, right? Yes. Okay, makes sense. So we have seen three central areas. Wait, too thick. Automata, computability, and complexity. If I remember right now, automata refers to machines. Computability, as names suggest, how much computation can be performed, I guess. And complexity is related to time complexity and space complexity. Automata, having a difficulty to write. Wait. Automata, computability, forgive my writing. I hope to improve my writing with continuous streams. Complexity theory. Computer problems come in different varieties. Some are easy and some are hard. For example, the sorting problem is an easy one. Say that you need to arrange a list of numbers in ascending order. Even a small computer can sort a million numbers rather quickly. And compare that to scheduling problem. Say that you must find a schedule of classes for an entire university to satisfy some reasonable constraints, such as that no two classes take place in the same room at the same time. Okay, you have to schedule classes such that no two classes can occur in same university in same class at the same time. I mean, it's that isn't reasonable at all. So the scheduling problem seems to be much harder than the sorting problem. Okay, if I have to schedule such that no two classes will occur in same room at same time, why is that problem hard? Let's say I have a university and it has many rooms. Okay, there are some rooms like these. Okay, and goal goal is to schedule two classes such that no two class will occur in same room at same time. And this problem is considered very hard. Let's see why. Let's say I have two classes. Class one is maths class, and class two is TOC class. Let's say some more subjects. Applied physics class, quantum mechanics class, and I have to organize all these classes in these rooms. Okay, uh, let's just make one more class. What can you make? Let's say the compiler design. I have to organize this like an algorithm. I can choose, let's say, one. This is one, room number one, room number two, room number three, room number four, room number five, six, seven, eight. Basically, ID of box refers to room number. And I have to, what I have to do is this room has the entire day, let's say 8 hour schedule, and that 8 hour schedule is occupied in 50-50 minute durations, 50 minutes of classes. Or let's say 45 minutes of classes. So you start at a given pool of time. The pool of time is, I take a pool of time. Pool of time is 8 a.m. to say 4 p.m. Yes, we have 8 hours. Pool of time is 8 hours, and every 45 minutes, I schedule a class. In room number one, I schedule, I check. Let's say I maintain a hash map, and that hash map will actually contain the subject tied to. But I'm hard coding it, right? But a scheduler should take any random object and schedule it somewhere. Okay. But if I hard code a timetable, then it is already easy. If I hard code a timetable, then it is already easy. Hmm. Restart. Okay, fine. A scheduling problem is considered hard because it involves combinatorial explosion, competing constraints, and NP hardness, meaning the number of opposite choices grows too fast to check by hand or computer in short time. Even a tiny problem with 10 tasks has 10 to power of 10 factorial possible orders, and adding more tasks makes the total number of options larger than the number of atoms in universe. Scheduling But why are you considering all possible? Why are you considering all possible orders? If I have a given goal to schedule something in some way, then I will prefer that way and limit the number of possible solutions. Why would I say all possible orders? NP hardness. Most scheduling setups belong to class of NP hard scheduling problems. Okay, no shortcuts. The number of ways to arrange classes, teachers, and rooms across time slots multiplies so fast that testing every combination would take a computer billions of years. Hard and soft constraints. But why do you have to uh, why do you have to check all possible combinations? For example, if I have a class registered, uh, I will maintain an entry for it, and I can search that entry. I maintain that entry in a sorted way, or I have a, let's say, uh, what do you say, indexed. I've made an index for it. Then, okay, systems must satisfy rigid limits while balancing preferences. Moving one single class to a different hour forces a chain reaction of changes across every connected teacher, student group, and room availability. Graph coloring mapping. Timetabling is mathematically equivalent to the graph coloring problem where conflicting classes cannot share the same color or same slot. A school has fixed number of classrooms and lecturers. A schedule cannot double book either lecturer or a classroom. So the timetable problem might be given a set of classes, okay, and classes includes like a set of lecturer, enrollment size, duration, and classrooms size, hours available. Here we have classes. Okay, ठीक है. Is there a schedule which accommodates all of those classes? Okay. Means you have a lot of classes, you have a lot of classrooms, and you have to schedule all those classes and all those classrooms in a way that there are no conflicts. Further elaborations are possible. For example, students may need to take a particular set of subjects to graduate, and then schedule should ensure this is feasible. Or we may also have some soft constraints where we would like to satisfy as many possible, such as leaving lunch hours open, distributing classes evenly, or working hour preferences of the lecturer. Some classes may need to be scheduled next to each other or not next to each other. To see that such problem is NP, we can observe that verifying the constraints, as long as they are not themselves complicated decision problems, can be performed in polynomial time. At the most basic level, given a solution, we just need to verify for every room and lecturer that it's not double booked. Oh, so what I was thinking, right? I was actually making a timetable and then thinking, I was actually making a timetable first and then associating it with that basically means I have an answer already, I have a timetable already, and I'm verifying. But the problem is not verifying, because verifying is easy. It can be done in polynomial time. And I was thinking that part. And we have to actually make that timetable. We have to make that timetable and not simply have the timetable and see. Okay. And let's say we have a timetable and we just schedule another class in the timetable, right? Maybe this is also hard to see such problem as NP observe. Okay. And every lecturer, every class was assigned in order to recognize that solution is valid, because the solution can be checked in P. Okay, that this isn't problem does a solution exist is NP. Does a solution exist? To prove NP hardness, a reduction to, you know what, I should actually know what is NP hardness first and then continue to research about this problem. So let me just read through the book somewhat more. Complexity theory. Automatic computing complexity. First year, see more complexity theory. Computer problems come in different varieties. Some are easy and some are hard. For example, okay, take what makes problems computationally hard and others easy. This is the central question of complexity theory. Remarkably, we don't know the answer to it. Though it has been intensively researched for over 40 years, later we explore this fascinating question and some of its ramifications. In one important achievement of complexity theory thus far, one of the many complicated or unexpected results of an action or decision. Okay. It's like just say an unexpected outcome of a chain reaction. In one important achievement of complexity theory thus far, researchers have discovered an elegant scheme for classifying problems according to their computational difficulty. So we actually don't know how to classify these problems as easy or hard. So we maintain, so we classify these problems according to their computational difficulty. And computational difficulty is measured in I think time complexity and space complexity, and it is analogous to the periodic table for classifying elements according to their chemical properties. Okay, it is analog. Okay, using this scheme, we can demonstrate a method for giving evidence that certain problems are computationally hard. So, what it means, I think, is that you have a like we have a periodic table of elements, and we can pick an element and uh, take it as a reference, let's say, and analyze whatever chemical reactions, compounds, and stuffs. Similarly, I think it is saying me that we have maintained a periodic table of hard problems, and we can reference those hard problems. And let's say if some given problem is referenced successfully to that periodic table, that means this problem is also hard problem. Okay. Yes, they have several options when you define. Using this scheme, we can demonstrate a method for giving evidence that certain problems are computationally hard. Okay, I'm right. Even if we are unable to prove that they are. You have several options when you confront a problem that appears to be computationally hard. First, by understanding the which aspect of the problem is at the root of the difficulty. Okay, now I know a given problem is hard. So how do I approach it? I approach it by first understanding which aspect of problem is it, the root of the difficulty. You may be able to alter it. Okay, whatever problem, matlab, whatever sub problem that bigger problem has at the root of the difficulty, matlab, whatever main broken part of that problem points to the fact that it is NP hard. I will take that sub problem and I will alter it so that the problem is more easily solvable. Second, you may be able to settle for less than a perfect solution to the problem. In certain cases, finding solutions that only approximate the perfect one is relatively easy. Okay. So it is saying me that I can basically approximate. First I can alter the problem to confront it. Second, um I can approximate to perfection. And third is some problems are hard only in the worst case situation, but easy most of the time. Okay. So in worst case scenario, I won't solve that problem for the worst case scenario. I will just solve it for other cases. Okay, depending on the application, you may be satisfied with the procedure that occasionally is slow but usually runs quickly. Finally, you may consider alternative types of computation such as randomized computation that can speed up certain tasks. You may be satisfied with the procedure that occasionally is slow but usually runs quickly. Finally, you may consider alternative types of computation such as randomized computation that can speed up certain tasks. Okay, this is interesting. Randomized computation. I just want to mm, mark this word. I don't know why. This sounds interesting because, you know, in computer science, nothing is truly random. Everything follows some order. And true randomness can be achieved only via, let's say, if we associate our algorithm, let's say, with climate change or weather and things like that. Because maybe, again, weather is uncertain. You don't know when what can occur. So you predict basically, and those predictions are also not every time 100% correct. That means it is kind of random. But let's say in future, if we totally make a formula that tells us that it's going to be sunny, it's going to be raining, whatever, then maybe true randomness will totally fail. Okay, so this word is fascinating me. That's why randomized computation. Randomized computation. Let's move further. When applied area that has been affected directly by complexity theory is the ancient field of cryptography. In most fields, an easy computation problem is preferable to hard one because easy ones are cheaper to solve. Cryptography is unusual because it specifically requires computational problems that are hard rather than easy. Secret code should be hard to break without the secret key or password. Complexity theory has pointed cryptographers in the direction of computationally hard problems around which they have designed revolutionary new codes. Computability theory. Okay, complexity we have seen an overview of complexity theory, which basically classifies problems. So what do I understand? What do I understand by complexity theory? Complexity theory. What do I understand by complexity theory? Complexity theory is basically classifying problems as easy or hard based on their computational difficulty, right? That was the right term, computational difficulty. Yes, classifying problems as easy or hard based on based on their computational difficulty. And it's like you maintain a periodic table of hard problems to refer at. And finally it said me how to approach. It also tells me, also defines ways to approach. It is hard problems. Should I also write alter it, approximate it, or what was the third? In other cases than first case. Now, coming to computability theory, during the half of 20th century, mathematicians such as Kurt Gödel Alan Turing and Alonzo Church discovered that certain basic problems cannot be solved by computers. Some basic problems cannot be solved by computers. One example of this phenomena is the problem of determining whether a mathematical statement is true or false. And this task is the bread and butter of mathematicians. Even- Are you sure? Matlab, that statement sounds like it is solvable by computers. Mathematical statement is true or false. It is a mathematical statement. So uh, I think it won't have semantic meanings. It will have a predefined steps to make it true or false, right? It seems like a natural for solution by computer because it lies strictly within the realm of mathematics. Yes, yes, I'm pointing exactly that. But no computer algorithm can perform this task. Okay, that is surprising. Okay. Among the consequences, this profound result was the development of ideas concerning theoretical models of computers that eventually would help lead to the construction of actual computers. Okay. The theories of computability and complexity are closely related. In complexity theory, the objective is to classify problems as easy ones and hard ones. Okay, I also wrote that. Whereas in computability theory, the classification of problems is by those that are solvable and those that are not solvable and not solvable. Computability theory introduces several of concepts used in complexity theory. And finally, coming to automata theory. Wait, computability theory. Why can't I draw a straight line? Yes. Computability theory classifies problems as solvable and not solvable. I think that is the only crux I can bring out from this paragraph, this set of paragraphs. Automata theory. Automata theory deals with the definitions and properties of mathematical models of computation. These models play a role in several applied areas of computer science. One model, called the finite automata, is used in text processing, compilers, and hardware design. Okay, so this is the precise thing you wanted to explore because, as I mentioned, I want to do compiler design and those stuffs. So, this is the subject of my study, but I have to study these things as well because uh, eventually all of those things merge at what is problem? What is a problem? Is that problem solvable or not solvable? And we approach to that question, we approach to that precise question in three different ways. First way is via complexity theory, second way is via computability theory, and third way is via automata theory. And automata theory precisely deals with such problems uh, by showing us different mathematical models and uh, defining properties of those mathematical models of computations. So coming to automata theory, it approaches problems by giving us mathematical models. It defines the properties of it defines and gives us properties. It it defines and gives us properties of mathematical model of computation. Various mathematical models of, I think my writing is improving, right? Example, finite automata. This is the plural form, right? No, this is singular form and automata is plural form if I'm correct. Automaton is used in text processing, compilers, and another model is called context-free grammar. Grammar. Man, have you forgotten the spelling? etc. The theories of computability and complexity require a precise definition of computer. An automata theory allows practice with formal definitions of computation as it introduces concepts relevant to other non-theoretical areas of computer science. So basically, automata theory will prerequisite both complexity and computability theory, if I'm correct. Fine. Yes, as it said, automata theory is the simplest to begin the study of TOC. Mathematical notions and terminology. As in any mathematical subject, we begin by discussion of basic mathematics, basic mathematical objects, tools, and notations that we expect to use. And when every basic mathematics chapter starts with sets, relations, and functions. Sets. Fine, I know what sets are, proper subject subsets. Multiset is you allow duplicates basically, right? This and this are different multisets but identical as sets. Fine. Infinite set. Fine. Fine. Equivalent of A. The intersection of A and B written as fine. Venn diagrams. You are defining a T, words that start with T, words that end with Z, words that start with J, and common part TJ, end J, end Z, or end start J. Okay, fine. Overlapping circles indicate common. Fine. Sequences and tuples. A sequence of objects is a list of these objects in some order. We usually designate a sequence by writing the list within parentheses. For example, the sequence 7, 21, and 57. Okay, fine. The order doesn't matter in a set, but in a sequence it does matter. And Different, okay, okay, order is different, does it is different, but insert will be same. As with sets, sequences may be finite or infinite. Finite sequences often are called tuples. A sequence with k elements is a k tuple. Okay. So in a k tuple, the order will matter. Thus, 7, 21, 57 is a three tuple, and a two tuple is called a ordered pair. Okay, that is a point to note, I think. The point to note is a sequence with k elements. A sequence of object in a list. A sequence is a list of objects in some order. A sequence is a list of object in some order, and then a sequence with k elements is a k tuple. Is a k tuple, and a two tuple is called ordered pair. Sets and sequences may appear as elements of other sets and sequences. For example, a power set of A, set of subsets of A, is a set of all subsets of A. Okay, fine, yeah, no. I'm zoning out a little bit. Sorry. If A and B are two sets, the Cartesian products. Okay, fine. I will just make the all possible. 1x, 1y, 1z, 2x, 2y, 2z, Cartesian products. Um, if A and B are, as in example 0.5, example 0.5, were there the examples 4, 3, 2? Wait, did I miss some examples? Hmm, this is weird. I don't see example 0.124 and suddenly I see example 0.5. Okay, there is figure 0.4 and then example 0.5. Weird convention. Uh, Mr. Sipser, if A equals, okay, that is basically Cartesian product. And in example 0.5, they did A cross B, right? And they are again crossing it with A. So this set 1x1, 1x2, then 1y1, 1y2, it's easy. Example 0.7. If we have a Cartesian product of a set with itself, we use a shorthand, simply represented as power. Okay. If set n square equals n cross n natural numbers, it consists of all pairs of natural numbers. You may also write it as fine functions and relations. Um, what was this form called? I think it is called set builder form. Set builder form. Am I correct with the term? And I set builder form. Yes, I'm right. Okay, set chapter is over so quick. Function and relation chapter is begin. Functions are central to mathematics. A function is an object that sets up an input output relationship. A function takes an input and out produces an output. Function is basically a machine. In every function, the same input always produces the same output. Fine. This is called a pure function. Same input, same output, pure function. If f is a function whose output value is b, and when the input value is a, we write a function of a is b. A function is also called a mapping, and if function with input a will give b, we say that function maps a to b. Okay. For example, if absolute value function abs takes a number x as input and returns x if x is positive and minus x if x is negative. Okay, it doesn't return. Oh, fine. Okay, it returns minus x if x is negative. Thus, it produces positive value. Thus, absolute value of 2 equals to absolute value of minus 2 equals to 2. Addition is another example of function written. Okay, the input to the addition function is an ordered pair of numbers, and output is sum of those numbers. The set of possible inputs to the function is called domain. Output is called range, and all possible set is called codomain. All possible sets and I mean the range. If range is a subset of another set, that another set will be called codomain. In case of a function absolute function, we are working with integers. The domain and range are z, so we write absolute. Okay, it will map integers to integers. Wait, can I not actually say that it will always produce output in whole numbers? So it will map actually z to w, or maybe I can also say n. More precisely would be w, because 0 equals to 0 absolute value, ain't it? Domain and range are z. Domain and range. Domain and range of abs function is z mapped to n, right? I mean w, sorry. No, that is incorrect. No, the standard absolute value function is r to r, or more accurately, well, okay. Domain and range facts. Range, the set of non-negative real numbers whose output are okay. If you are taking only discrete values of whole number, or basically integers, then you are going to get whole numbers, yes. But absolute value of, let's say, minus 2.4 is 2.4, right? And 2.4 is not whole number or not natural number, so only set it can include is real number, so r to r is r to r makes sense. I don't know why it has said z to z then. In case of addition function for integers, the domain is set of pairs of integers, and the range is k. It's fine by me. A function that does use all the elements of its range is said to be onto the range. Hmm. Shouldn't you say it like a function that does use all the elements of the codomain is said to be onto the codomain? We may describe a specific function in several ways. One way is with a procedure for computing an output from a specified input, and another way is with a table that lists all possible inputs and gives us the output for each input. Okay, don't you think both are same? List of all possible inputs. I mean, in first way, you are just calculating answers one by one, and in second case, you are like, what do you say? You are taking a batch of numbers and then producing output. So again, in that batch also, you will find the answers one by one, right? So what's the matter? Consider the function. Oh, oh, okay, I understand. They could have written it like f of 0 to, let's say, 1, or let's say whole number to whatever. This is like whole number to whole number, but they have specified a particular set of elements, and those particular set of elements are mapped to another particular set of elements, not an infinite set. This is a limited finite set. This function adds 1 to input and then outputs the result modulo 5. A number modulo m is the remainder after division by m. Okay, huh. For example, the minute hand on a clock face counts modulo 60. When we do modular arithmetic, we define, okay, with this notation, the aforementioned function f has the form z5 to z5. It does make sense. Sometimes a two-dimensional table is used if the domain of the function is Cartesian products of two sets. Domain of the function is Cartesian product of two sets. Here is another function. You have a function is g, and that function, I would like to write different notations here. And, my maths was always weak. I should study harder. Okay. Let's say you have a function. I'm basically writing different notations. Different notations. Functions. First that I see here is like f, let's say an infinite set to infinite set. Okay. Then let's say you have a finite set 0, 1, 2, 3, 4, and that is mapped to 0, 1, 2, 3, 4 yet again. You can also write functions like Cartesian product of two sets. Let's say modulo 4 function. This is modulo 4 function, modulo 4 whole numbers combined with modulo 4 whole numbers, and they produce modulo 4. The entry at row labeled I and the column labeled J in the table is the value of G I comma J. Basically, this function takes two inputs and produces an output. See, this is first input access, this is second input access, and this is basically giving me final output. Add one and what was the idea? Add one and do modulo 5. So 0 plus, okay. I think it is doing like 0 plus 0 and 0 plus 1, 1 modulo 5, 1 plus 6 modulo 5 is modulo 4. Okay, sorry. Modulo 4. Fine. When the domain of function f is, wow, for some sets, okay, the input to f is k tuple. Input to f is k tuple. Yes. And we call ai the arguments to f. The function with k arguments is called a k array function. And k is the arity of the function. If k is 1, f is single argument, and if k is and f is called a unary function. And if k is 2, it is called a binary function. Certain familiar binary functions are written in a special infix notation with the symbol for function placed between its two arguments rather than prefix notation with the symbol preceding. For example, the addition add is usually written in infix notation with plus symbol in between two arguments. This paragraph has a lot of information. Mm. Let the domain of a function be a1, a a viewers will not be able to see. A1 ak. Of course, the sets are those. Means domain of function f b. This means input of f is a k tuple. A function with A arguments is called a K array function. K is the arity of the function. Ternary function and so on. Then there is something called prefix notation in which something called infix notation symbol in between arguments. A binary function has infix notation and a prefix notation. In this infix, a predicate or property is a function whose range is k. For example, let even be a property that is true if input is even number and k. There are a lot of definitions now in the book. Predicate or property is a function whose range is true and false. Example, even property, odd property. A property whose domain is set of k tuples. Set of k tuples means that there is a literal set of, and when each element is a k tuple. Wow, is called a relation. A property whose domain is a set of k tuples is called a relation. A k array relation or a k array relation on A. A common case is a two array relation called a binary relation. When writing an expression involving a binary relation, we customarily use infix notation. For example, less than is a relation usually written with the infix operation, symbol less than equality is written with equals to symbol, and in another familiar relation, if r if r is a binary relation, the statement a r b means that a r b equals to true. Similarly, if r is a k-array relation, the statement k means that equals to true. This part is something that has gone out of my brain. Okay. In a children's game called Stone Paper Scissors, okay, the two papers simultaneously, two players simultaneously select a member of the set, okay, and indicate their selections with hand signals. If the two selections are same, the game starts over. The game starts over. If selections differ, one player wins according to the relation beats. And what are the beats? If scissor comes with scissor, false. Scissor comes with paper, true. Scissor comes with stone, fail to false. Paper with scissors, scissors wins. This is false, no? And this loses, right? The false. Paper with paper, false. Paper with stone, true. Stone with scissors, true. Stone with paper, false. Stone with stone, false. From this table, we determine that scissor beat paper is true and that paper beat scissors is false. Sometimes describing predicates with sets instead of function is more convenient. May be written as ds, where a belongs to d and p of a is equals to true, or simply s if the domain d is obvious from the context. Hence the relation beats may be written. I think today I'll only study till okay. How much time is 12 more minutes only. Right. Sometimes describing predicates with sets instead of functions is more convenient. Why? The predicate player, it's D. Domain, true, false, may be written as where S is a set such that includes all the elements where A belongs to D and P of A is true and P is function, that function, see this function, or simply S if the domain D is obvious from the context. Hence the relation beats may be written as hmm, beats may be written as this. How? Actually, you have taken only true elements. Scissor paper, paper stone, and stone scissor. Only these are true and rest all are false. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. If special type of binary relation, F is true. A special type of binary relation is called an equivalence relation, captures the notion of two objects being equal in some feature. A binary relation R is an equivalence relation if R satisfies three conditions. RST, reflexive symmetric transitive, I know that. Define an equivalence relation on natural numbers. What is this written? For I, J belongs to natural number. Say that I don't understand what is this written. What is this? If I minus j is multiple of 7, this is an equivalence relation because it satisfies the three conditions. First, it is reflexive as I minus I 0. I need to understand the meaning of that symbol, whatever. When will AI help? The symbol is, okay, it is read mathematically as congruent modulo. Congruent modulo. The triple bar denotes congruence or equivalence relation. The subscript R specifies the modulus of that relation. To put this theoretical concept into practical terms, okay, equivalence relation translates to logic into Python. Is congruent mod 7. Checks if I and J are congruent modulo 7. Okay. For I comma j belongs to natural numbers is that is relation congruent modulo relation, right? Congruent modulo 7. How do you read it? Let's say I say I. How do you read it? You read it I is congruent to j modulo 7. simply mod 7 for short. ing, the numbers being compared, is congruent to, meaning they share the same equivalence class, and modulo 7, which means the rule defining the equivalence class, congruent to j modulo 7. If um, say that I is congruent to j with modulo 7, if I minus j is multiple of 7, there is an equivalence relation because it satisfies the three conditions. First, it is reflexive, means all the same elements, let's say both numbers should be same. It gives 0, which is a multiple of 7. Okay. Second, it is symmetric. If ij is a multiple of 7, j minus I is also multiple of 7. Yes, fine. As whenever I minus j is multiple of 7 and j minus k is multiple of 7, then I minus k, that is equal to I minus j plus k. Let me test this one. If I have, what do I have? Define a equivalence relation on natural numbers. Natural numbers for I, comma j belongs to natural number set. Say that I, j, I minus j is it is obvious, very obvious that it is reflexive and symmetric. But what about transitive? If I have two numbers, let's say one, let's just say multiple of 7, right? Natural number set. I take two numbers as 16 and 2. 16 minus 2 satisfies this. Another set, let's say 9 comma 2 satisfies this. So 2 comma 2, yes, 2 comma 2 also satisfies this. Okay, no. 16 2. Let's take another example, like if this is satisfied, it is symmetric, right? So 2 comma 9 will also work. If I take I just took wrong example basically. This is the right example of transitive. These two elements should be same. So 16 minus 9 is basically equals to 7. Wow, that's amazing. If I add sum of two multiples of 7, sum of two multiples of 7, okay, that makes sense, and hence a multiple of 7 too. That very much makes sense. This is something I don't need. Reflexive. Positive. I think that is it for today. Maybe I can introduce myself to crafts because some time is still left for this stream. No, actually, 1 or 30 minutes have passed already. So let's continue graphs in next stream. What do I have to cover? There are a lot of graphical concepts. So I have completed sets, relations, and functions, and now graphs, then strings and languages. Okay, this is interesting. Then Boolean logic. What is this symbol? Implication. Okay, okay. These definitions are amazing. Definitions, theorems, and proofs. Finding proofs. Theorems. It is actually like figures, examples, theorems, all are confined in a same set of numbering order. 0.19 example and theorem 0.20. This is De Morgan's law, right? De Morgan's theorem. For every graph G, the sum of the degrees of all nodes in G is an even number. Okay. Types of proof by construction, by contradiction. Okay, I know the contradiction one, but I haven't heard of construction. This is something new. And huh, root 2 is irrational is a theorem. Okay, reduction step for each t is greater than 0. Why do I feel like I'm studying heat equations in physics? Something about thermodynamics. What was that? Uh, Something with A, PV to the power gamma. I I just remember. Okay, I don't know what is this trying to represent. Okay, we have exercises as well. Examine the following formal descriptions of sets so that you understand which members they contain. Write in a short informal English description of each set. Okay, that's easy. I think this is simply odd number set. Informal description done. This is even integers description done. We'll see for these right formal descriptions of following sets. Formal description and informal English description. I think by formal descriptions you want me to you want me to make a set builder form. Let A be this, B be this. Questions are good. Okay, 10. How many questions are there? What does this mean? We have total 15 questions and then we reach chapter 1. Okay. This is going to be amazing. We are going to study graphs and definitions, theorem proofs, languages, things like that, and how to find proof, how to uh, find by, let's say, contradiction and what was it, construction. And finally, we have some exercises which include 15 questions, graphs. So, see you in next stream. Thank you for watching. Thank you for supporting me. Bye.